Okay, so today we're going to be talking about the ratios of similar solids. So a few definitions to get us started. Similar solids have exactly the same shape. So they're the same shape. They're similar to each other, but not the same size. That's why they're not congruent. They're just similar. They have the same shape, but not the same size. Two solids are similar if the ratio A to B of their corresponding linear dimensions are equal. Okay, so we want to see if we compare their corresponding linear dimensions, are they equal? So when we say linear dimensions, what are we talking about? Examples of linear dimensions are length, width, height, radius, diameter, slant height. So these would all be dimensions, linear dimensions of figures. Some other linear measurements, they aren't actual dimensions of the objects, but they are linear dimensions that can also be equal, would be perimeter and circumference. Those aren't strictly dimensions because you have to find them, sum them. They're not just an individual measurement, circumference. But those ratios could also be equal. Okay, so identify the scale factor and the ratios for each pair of similar solids. So if we want to compare similar parts, so here I can see the height of the figures. So if this is the larger of the two figures, I want to always put the larger height on top and compare its ratios to the smallers. I could do smaller to larger. I just want to be consistent about always putting them in the same place. So its height is 12 to the 3 in the smaller when we're comparing height. Okay, and we're going to see what that simplifies to. Then we're going to compare its width to width. Okay, so we just looked at height to height. When we do width to width, we're still going to compare larger. So 8 to smaller, 2, and we'll see what that simplifies to. And I guess I could call this the length. So we're going to go length to length. Again, larger to smaller, so 20 to 5. And if these are similar, then all of the ratios of their linear dimensions, when we compare corresponding parts, will be equal or congruent. Okay, 12 over 3, 3 goes into 12 4 times, that simplifies to 4 over 1. 2 goes into 8 4 times, that simplifies to 4 over 1. 5 goes into 20 4 times, that simplifies to 4 over 1. So the scale factor is a ratio of 4 to 1. And we can write it as a fraction, but it's also very common to write it with a colon in between. So it's a ratio of 4 to 1. This is obviously the ratio of larger to smaller. We could write it 1 to 4, and then it would be a ratio of smaller to larger. Okay, let's check this next figure and see if it's similar. So again, we want to label those corresponding parts to make sure we're comparing corresponding parts. I think I'll call this the height. Remember, on rectangular prisms, it depends on how you look at it. And I'll call this the length and this the width. Okay, so we want to make sure we compare height to height, width to width, and length to length. And then we'll see if they simplify down to be the same thing. So I'm going to go this time because smaller is first. I'm going to go smaller to larger. Again, you could do it either way, but you want to be consistent. So 8 to 12 on the height, 6 to 10 on the length, and 6 to 10 on the width. So that's a square prism because it's the sides of the base are all the same size. Okay, 8 over 12, 4 goes into 8 2 times, and 4 goes into 12 3 times. So that simplifies to 2 over 3. If we look at 6 over 10, 2 goes into 6 3 times, and 2 goes into 10 5 times. And right there, I see I have a problem. 2 to 3 is not equal to 6 to 10. So these are not equal. So I can just stop right there. Therefore, they are not similar. They're not similar. If they don't simplify down to the ratios, or if the ratios are not equal of their corresponding linear dimensions, then they are not similar. So this one is not similar. Okay, even though if I had kept going, 6 over 10 again would also simplify to 3 over 5. It doesn't matter that 2 of them are equal. All of their corresponding linear dimensions have to have the same ratio. So this is not similar. So this one was similar. This one's not similar. Okay, so if we want to compare the volume and the surface area, so this is kind of what's a new idea to us. We've done similar triangles before, so we know how to compare those corresponding parts to see if they're similar. Now we're just doing it with three-dimensional objects. So we're ready to extend to different measurements as well. If two objects are similar, then with a scale factor of A to B, and again, those are just variables that we use to represent the ratio of the corresponding linear measurements. Okay, so of A to B, then then their volume and surface area ratios are: surface area will be A squared to B squared. And again, that makes sense because area is square units, and so that can be kind of a logical connection for us. And the volume will have a ratio of A cubed to B cubed. And again, that makes sense because we think of volume as cubic units. So this will be kind of easy to remember and important to remember. We see this a lot on ACT and SAT questions. Okay. Identify the scale factor ratio for each pair of similar solids. Okay, so I want to compare corresponding parts. So I'm going to call this the height of the triangle. So we want to compare height to height. And then I'll call this length and length. And then this is the height of the prism. So I'll call that H sub P for height of the prism. It's a triangular prism. Height of the triangle is the first one. So I'll indicate that the height of the triangle. Okay, and we just want to compare them and see what they are. So height of the triangle, I'm going to go the big to little. That's big to little, okay? Being consistent every time. So that's going to be 6 to 3. Again, keeping it big to little. When I compare the lengths, it's going to be 14 to 7. And when I compare the heights of the prism, that's going to be 10 to 5, okay? So a lot of you probably could see it as you were writing it in your head. That does simplify down to 2 over 1. That simplifies down to 2 over 1. And that simplifies down to 2 over 1. So the scale factor is a ratio of 2 to 1. Now, if they cared about the order, then they would tell you the scale ratio of larger to smaller. If you wrote 1 to 2 here, that would be acceptable because the directions don't specify, but usually they do specify. Okay, now, if they have a comparison of 2 to 1, then their surface area will have a comparison. Remember, this is A to B. So the surface area will be A squared to B squared. So for us, that's 2 squared, or 4, to 1 squared, which is still 1. Okay. The volume of the ratio will be A cubed to B cubed. So again, that's 2 cubed, which is 8, to 1 cubed, which is still 1. Now that's interesting. When you get one behaves differently than other numbers. So we see that here by this indicator. At the cones. So if we're going to compare, this time I think I'm going to compare the small to the large. I write that as the side just to remind me. And so I want to compare the radii to radii. and the slant height to the slant height. So I'm going to do those just to make sure I'm comparing the right things. Okay, so that's going to be 4 to 6, which simplifies down to 2/3. And when I compare the slant heights, that's going to be 7 to 10.5, which also simplifies down to 2/3. Okay. You can check that on your calculator to see. So the scale factor is going to be 2 to 3. Remember, if they didn't simplify down to the same thing, then they would be not similar, and you can check that by plugging it in your calculator. Okay, so if this is our scale factor A to B, then the scale factor for surface area, because area is square units, is going to be A squared to B squared. And so that's going to be 2 squared, which is 4, to 3 squared, which is 9. Okay, for the volume ratio, it's going to be A cubed to B cubed. And so that's going to be 2 cubed, which is 8, to 3 cubed, which is 27. Okay, so here we have two figures where they started by giving us one of the other units. So here they gave us our surface area is 25 to 4. So if I write that as a ratio, that's 25 to 4. And because this is surface area, I know this is my A squared to B squared. Okay, so if the surface area ratio is 25 to 4, and I want the scale factor, then notice that I'll have to do the square root of it to get back there. So if I know A squared to B squared, then I have to undo a square with square root. So we're going to do the square root of both of those to get back to A to B. Okay, so the square root of 25 is 5. The square root of 4 is 2. So the original scale factor would be 5 to 2. Let's take a look at it with the next shape. So here they gave us the volumes. And so if I write that as a fraction, the volume is 162 over 384. If you use your calculator, that simplifies down to 27 to 64. Okay, so that's the volume ratio, 27 to 64. Now remember, the volume ratio is A cubed to B cubed. So if I want the scale factor is just supposed to be A to B. So how do we undo a cube? With a cube root. So we're going to take the cube root of both of those. The cube root of 27 is 3. The cube root of 64 is 4. So the scale factor is 3 to 4. If they asked us for the area ratio, now that we have the scale factor, 3 to 4, we could just square those numbers to get the area ratio if we wanted. What if we just change one dimension? So I think it's pretty easy on what we were just talking about, how it's A to B and then A squared to B squared for area and A cubed to B cubed for volume. But what about changing dimensions? If the dimensions of a solid are multiplied by a scale factor of K, K is usually the variable used for scale factor, then the surface area is K squared times the original surface area. And again, that makes sense because it's area, and so we're used to that being square units, so it's going to square the dimension change as well. And volume is K cubed times the original volume. So let's take a look at how that would work. Okay, slightly different kind of problem. If the dimensions of a figure are doubled, okay, if the dimensions of a figure are doubled, that means they're multiplied by 2. So 2 is my K value there. So here K equals 2, okay? How many times larger will the surface area be? Well, we know that the surface area will be K squared times larger. So that's going to be 2 squared, which is 4 times larger, 4 times larger. Okay, let's try the next one. It says the surface area of a figure is 736 inches square. If the dimensions are multiplied by 1/4, okay, so here my scale factor is 1/4. The dimensions It says dimensions are multiplied, okay? So just like in the first one, you want to be looking for that term. The dimensions are doubled, okay? The dimensions are multiplied. That means we're using the scale factor of k instead. What will be the surface area of the new figure? Okay. Well, they want the surface area, so that means that the surface area will be k squared times the original. So k squared would be 1/4 squared. When we square a fraction, we square everything in the parentheses. So we do 1 squared over 4 squared. So that's going to be 1/16. So it's going to be 1/16 of the original. So then we can just do 736 times the 1/16. And we get that the new area will be 46 inches squared. Remember, we still want units, okay? And that's the surface area of the new one, okay? And so that's square inches. If the dimensions of a figure are multiplied by 4, okay, so did you see the keywords to tell us how we're going to work this problem? It says the dimensions are multiplied by 4. That means we're talking about a scale factor here of 4. So the scale factor is 4, okay? How many times larger will the volume be? Well, we know volume is cubic units, so it'll be k cubed times bigger. So what is 4 cubed? 4 cubed is 64, so it'll be 64 times larger. Okay, so notice the different kind of question. If they're just asking how many times larger it'll be, then you just have to get the k cubed, and that's your answer. On the last example, they asked us, what will the surface area be? So once we found out how much bigger or smaller it would be, it was going to be 1/16 the original. Then we had to actually multiply it by the original to find the actual. Okay, so do they want to know how many times larger it is, or do they want to know the new resulting unit? We can handle it either way.